Hi everyone, my name is David and I'm going to be giving a lecture on naming and isomers today. So like I said before, this lecture is being recorded and also posted on YouTube. So if you don't want your images on your Zoom profile picture or your name part of the recording, if it is in it at all, then please change your name or your profile picture. You can give this a read if you want. This will be in the lecture slides. So just a quick description of the course. It's a 15-week MCAT course. I believe we're on week 9 right now. We do lectures on MCAT topics using Zoom every Thursday, Friday, and Saturday at 8:30 p.m. EST. And then every Sunday at 8:30 p.m. also. We do office hours. If you have any questions or you want to go over any specific problems, we can help you. And here's just some useful links if you want to check them out. So we do have a group meet chat if you're not in it already. There's a few hundred students in there and the tutors are in there also. If you want to post any questions or ask anything, you can on there. And then we do, like I said before, we do have the YouTube channel where we're posting the actual recording of this video. And then we also cut up the videos into smaller topics if you want to give that a watch. And then also we have this website, socraticmake.net. You can check that out. They post all the lectures on there also, and then more general information about the program. And then we also have an Instagram if you want to give it a follow. They post reminders about the lectures and more general information, and also any opportunities for other non-MCAT related stuff, more like medical based opportunities. So you can check those out if you want. And then for the learning objectives for today, I'm going to go over how to name the compounds that will be on the MCAT, and also how to identify them using the IUPAC naming system. And I'm also going to go over chirality and then use that to determine R or S configuration for molecules. And then finally, I'm going to go over the different types of isomers and the specific characteristics of each isomer. So first thing, I'm going to go over naming. So on the MCAT, they use the IUPAC naming system. It's called the International Union of Pure and Applied Chemistry. You don't need to remember that long name. Just know the IUPAC. So whenever they say IUPAC, this is what they mean. They use this system because it creates an unambiguous relationship between the name and the structure of a compound. So that means each compound, specific compound has a specific name, and no two distinct compounds have the same name. So each name of a compound relates to a specific compound. And so we mainly use this to name long carbon chains on the MCAT. And so for the MCAT, you're going to need to be able to identify the structure of a compound from its name, and then also be able to identify what the name is just by looking at the compound. So first thing, when numbering the carbon chain, you have to identify the longest carbon chain with the highest functional order group. So the carbon chain, it may have a lot of branching. So you have to count the longest chain in that molecule, and that will be used as the suffix of the name. And the longest carbon chain has to contain the highest order functional group. So if it's like a long chain with an alcohol, just an alcohol or a hydroxyl group on it, you have to include the hydroxyl group in its name. So like I said, the parent chain, it determines the root of the IUPAC name. And when looking at a molecule, you have to consider double and triple bonds when identifying the highest order functional group. So if the molecule doesn't have anything attached to it, just carbons, then the double and triple bond will be considered the highest order functional group. So you have to consider that when choosing the name of the molecule if you're asked to identify it. So the highest order functional group, that's the group with the most oxidized carbon in that molecule. And that's, like I said, used to identify the suffix of the name. And if there are two or more chains of equal length in that molecule, to determine which chain gets priority as the parent chain, you have to identify which chain has the more substitute chain. So whichever chain has the most substituents attached to it will be given priority as parent chain. So next, you have to number the carbons on the chain. So carbon number 1 will be chain closest to the highest priority functional group. So like I said, if the chain has an alcohol on it, carbon number 1 will be the carbon closest to the hydroxyl group. But if all the functions groups have the same priority, then the more substituted carbons will give the lowest numbers possible. So if there's a long chain with 2 substituents on one carbon and then 1 substituent on another carbon, then you want to give those carbons the lowest number possible when numbering the carbon chain. And that relates to how the most oxidized carbons have the highest priority. So just to go over oxidation states, it increases when the carbon has more bonds to hetero atoms, which are atoms besides carbon, hydrogen. So like oxygen, nitrogen, anything more electronegative than carbon. And then those will increase the oxidation state. And then carbons that have less substituents and more bonds to hydrogen will have a decreased oxidation state. So the more oxidized carbons will be the ones with higher priority because they're more oxidized. They'll have more bonds to oxygen, nitrogen, all those electronegative elements. And that will cause it to have a higher priority functional group when compared to carbons with only bonds to hydrogen or no substituents at all. So just to go over, you see this top molecule when deciding the name of the chain, you have to look at the longest chain. So on the top, you see here, this in the carbon chain in the red box, it has 8 carbons in it. That's more than any chain you can create using the other branches of carbons. So that would be the longest chain in this molecule. So that would be used as the suffix of the parent chain. You see how the other branchings still only have like 1 or 2 extra carbons instead of this 8 carbon chain. And then, like I said before, when numbering the carbons, you have to give the highest priority function group the lower numbers. So on the left here, the 3, 4, and 5 carbon has substituents attached to it, right? So you want to give that the lowest number possible for these carbons right here. The other way would be the right side, which is incorrect because this numbering gives the substituted carbons the numbers 4, 5, and 6, which are higher than the left side, which is 3, 4, 5. So the left side would be the correct one, not the right side, because of the numbering system. So whenever you give numbers to carbons, you want to give the highest priority functional group more precedent than the lower priority functional groups. So the carbons closer to the higher
the Taliban remain misogynistic. President
sorry. Who, did someone say something? Okay. Yeah, so like I said, left side is correct, right side is wrong, because the right side, it has the higher numbers for the more substituted carbons. And then for rings, they're numbered the same as carbon chains. The point of greatest substitution is the start of the ring, because you want to give the lower numbers to the carbons with carbons closer to the higher priority functional groups. And then you continue in the direction that assigns the lower numbers to the more substituted carbons. So in this ring, you'll give the carbon number 1 to either carbons attached to the chlorine, and then you would give carbon number 2, assign carbon number 2 as the other one attached to chlorine. So that makes sense, because since they're next to each other, you want to give them the lower numbers. So there'll be 1 and 2 instead of going around the other way, and it'll be 1 and 6. All right, so let me just write this here. So you want to give this 1 and then this 2, 3, 4, 5, 6, instead of going the other way around where you give this 1 and this 2, which would lead to this carbon being number 6. So 1 and 2 would be smaller numbers than 1 and 6. So that's why you number it the first way I showed. So next, I'm going to go over the prefixes. So after you identify the carbon chain, you will have to add prefixes and suffixes to the name. So usually the prefixes we use are dot. Usually, if it's just one, you can write mono, but usually they don't specify mono. So, but they use di, tri, and tetra when there are multiple substituents of the same type. So you add that in front of the substituent's name. So when there are 2, you use di, 3 tri, and 4 tetra, and so on. So 5 penta, 6 hexa. So this is whenever you have multiple substituents of the same type. So if you have 2 of the same alcohol, you can use dihydroxy or trihydroxy if there's 3. So that's the prefixes, and I'm going to go over how to name the substituents. So substituents are functional groups that aren't part of the parent chain. So anything that branches off from the parent chain, we have to identify them as substituents and then add that into the prefix of the name of the molecule. So like I said, the name is placed at the beginning of the name as a prefix, followed by the name of the longest chain. And even the substituents, you have to assign numbers to them based on the carbon they're attached to in the chain. So if they're on carbon 3 in the chain, then you have to add the number 3 in front of the substituent. So yeah, you pair each of the substituents to the corresponding name in the parent chain. And like I said before, if there are multiple substituents of the same type, you have to use the di, tri, tetra, and so on prefixes and the carbon number designation before the name of the substituent. Yeah, and so in the parentheses, it says even if they're on the same carbon. So if you have 2 alcohol on the same carbon, if they're both on carbon number 3, you have to use 3, 3 dihydroxy. So you have to specify the number of carbon for each single substituent. Okay, so if the substituent is an alkane, a carbon chain, you do that by replacing the suffix YL. You replace the suffix ane with the suffix YL. So instead of methane, it would be methyl. Instead of ethane, it would be ethyl. And sometimes they include the prefix N to it to specify normal straight chain alkanes, but usually they don't. So if the carbon chain doesn't say N in front of it, you can just assume it's a normal straight chain. So on the right, I just have a list of some of the more common alkanes that would be used as substituents. Usually they use methyl, ethyl, propyl, sometimes isopropyl and butyl, and then tert-butyl sometimes too on the bottom. And if the carbon chain has any double and triple bonds, you have to name that in the substituent also. You also have to indicate the number of the carbon they're on. So you can do it two different ways. You can have the number before the name of the carbon chain, so 2, which is where the double bond starts, and then butene to specify there's a double bond in the carbon chain. Or you can put it near the suffix in between the name, so 2, so but to specify the length of the chain, 2 specifies where the chain, the double bond starts in the chain, and then ene to specify there is a double bond in the chain. On the MCAT, they'll use it either ways. And if there are multiple double or triple bonds in the molecule, you have to specify where it is. So if there's a double bond starting at 1 and then a double bond starting at 3, you have to write it as 1, 3 butadiene. So that specifies there's a double bond at 1, carbon 1, there's double bond at carbon 3. The length of the chain is a butane, and then the di signifies that there's 2 double bonds in the carbon chain, and then the ene specifies there is a double bond in the carbon chain. So they're very like specific about everything. When naming, you have to identify everything that's in this molecule, and this is why there are no 2 molecules that have the same name but look differently when drawn out. And other substituents. So for alcohol, you use the prefix hydroxy when it's not part of the parent chain. And for ketones and aldehydes, you use oxo for both. So for aldehydes and ketones, you can use oxo as the substituent name. Sometimes they use keto for ketones. Okay. And then for suffixes, they can suffixes, it's determined by the highest priority functional group in the carbon chain. So after you identify the carbon chain, if it's just an alkane, just hydrocarbons with only single bonds, then you just add an ane at the end as a suffix. For alkenes, anything with a double bond in the chain, you add the ene at the end. And then for alkynes, the chain has a triple bond, you add ine at the end. Sorry, hold on one. Sorry about that. Yeah, so those are for the hydrocarbons, single, double, and triple bonds. And then if the highest priority functional group is an alcohol in the chain, you can name it by replacing the E in the alkane name with OL. So instead of methane, it would be like methanol, ethane would be ethanol. And then you would number the carbon attached to the hydroxyl group with the lowest possible number. That's to to signify that the alcohol group is the highest priority functional group. So you would specify it with, you would assign it the lowest number possible. And they can also name it by having the alkyl group and then followed by the word alcohol. So for ethanol, it could also be called ethyl alcohol. On the bottom, I just have some common alcohols that you might see. So methanol or methyl alcohol, ethyl alcohol, which is also ethanol, propanol or propyl alcohol, and then isopropyl alcohol, that's less common. And then for molecules with multiple alcohol groups, so for diols or glycols, they have 3 alcohol groups. You can use the suffix diol instead. So this is any alcohols with 2 hydroxy groups. When they have 2, you have to still specify where the position of both the alcohols are. You have to number the hydroxy groups. So for example, for an ethane with 2 alcohols, you would name it ethane 1,2-diol. So you number where the 2 alcohol groups are, the 2 hydroxy groups are in the alcohol. So the first one would be at carbon number 1 and then carbon number 2, and then you add diol at the end to specify that there's 2 alcohol groups in this parent chain. And then when the highest priority functional group is an aldehyde, it's a carbonyl at the end of a carbon chain. I put the structure on the right to show you. So since it's usually attached to, since it's at the end of a carbon, usually it's attached to C1 because if there's no other higher priority functional group, then it's the highest priority functional group. So then since at the end of a carbon chain, you usually number that carbon 1, and then go upwards when naming the other carbon. So the carbon next to it would be carbon 2. So this R group, the next carbon would be carbon 2, and then 3, and then 4, so on. And when it's at carbon 1, usually they don't number it because they just assume that it's at the first carbon. So for methane with an aldehyde group attached to it, it would be called methanol. Ethane would be ethanol, and then propane would be propanol. So that's for aldehydes. For ketones, the carbonyl is in the middle of the carbon group, right? So you have to number that. You have to specify which carbon it's on. So when you assign the number to the carbonyl carbon, you have to identify that in the complete name of the group. And when it's the highest priority functional group, you have to replace the parent alkane. You have to replace the E in the parent alkane with a suffix "-one". So instead of like ethanol, it would be you would need a propane. So instead of propane, it would be propanone. And so ketones, they'll have the alkyl groups attached on either side of the carbonyl carbon, and you have to list those also. So you usually list the alkyl groups in alphabetical order, followed by ketone. So if it has like ethane and then a methane attached to it, you have to specify that in the name and then just add ketone as a suffix. And then next, carboxylic acids. That's usually on the first carbon, and they're pretty oxidized since the carbon has 3 bonds to oxygen. So it's usually the highest priority functional group in the molecule. And to name the carboxylic acid, you take the parent alkane name and replace the E at the end, and you add the suffix oic acid to it. So instead of methane, it would be methanoic acid, ethane, ethanoic acid, propane, propanoic acid. And on the right is just the structure of the carboxylic acid, the basic general structure of it. And then ester, so those are usually created by reactions with carboxylic acid and an alcohol. You take the alkyl name of the esterifying group, so usually the alcohol, and then you usually replace the oic in the name of the parent acid with OA. So if it's a, let's say, methane attacking this carboxylic acid to create this ester, you would call it methane, methyl, and then whatever acid it is, methyl propanoic acid, if it was propanoic acid attacked by a methanol. And then on the general, on the right is just the general structure of an ester group. So you can see on the left side is the structure of a, on the left half of this molecule is the structure of a carboxylic acid, and then on the right is the structure of an alcohol group, And when those two react with each other, they create this ester molecule. Next, I'm going to go over amides. So for amides, when you want to name it, you have to replace the suffix with amide. And then, as you can see on this picture on the right, the nitrogen usually has two R groups attached to it. You have to name those as substituents for the nitrogen atom. So you have to label it with a capital N to specify that it's bonded to the parent molecule via the nitrogen. So don't confuse that with the lowercase n that signifies a normal straight chain for the alkane. So the capital N means that it's the substituents are bonded to the nitrogen atom via the nitrogen. The substituents are bonded to the nitrogen atom, and that's how they're connected to the whole parent chain. And usually you don't number the substituents because they're attached to the nitrogen, so they wouldn't have a number since it's not bonded to a carbon. And lastly, anhydrides. So these are created by reactions of two carboxylic acids. So to name it, you have to replace the suffix acid of the carboxylic acid with anhydride. When there's only one type of carboxylic acid, you can just replace the acid with anhydride. So if it was propanoic acid, you could just call it propanoic anhydride. But as you can see here, these two carboxylic acids, before they form, they have R groups attached to it. So if the R groups are not the same, if the anhydride is not symmetrical, then you have to name both carboxylic acids in the name. So that's for anhydrides. Yeah, so in order to have the complete name, you begin with the name of the substituents in alphabetical order with the number of the carbon that the substituents are on. And usually the substituents are named in alphabetical order, but if they have a prefix like di, tri, tetra, n, or tert, those are ignored when alphabetizing. But when the prefix is actually part of the name, so any non-hyphenated roots that are part of the name, like iso, neo, cyclo, you have to consider those when alphabetizing the substituents. And then the numbers of the carbon they're on are separated by commas, and then separated from the substituent name using hyphens. And then next you add the name of the carbon backbone chain, and then you finish off by including the suffix of the functional group with the highest priority. So this is how you get the complete, this is just like the general instructions for figuring out the complete name if you're given a molecule. So just an example, in this molecule, after you find out the longest carbon chain in the molecule, you use that for the name of the parent chain. So this 8 carbon chain is the longest chain in this molecule. So it would be octane in this name. And then you see the substituents branching off from the carbon chain. You have the numbers of those two. So you would start with carbon number 1 on the left side because it would assign these carbons with the substituents a lower number than if you started numbering from the right side. So on carbon number 3, there's 2 methyl groups. On carbon number 4, there's an isopropyl group. Carbon number 4, it's an ethyl group. And then on carbon number 5, it's an isopropyl group. So those are the substituents branching off from the carbon chain, and you have to list them in alphabetical order. So ethyl, isopropyl, and then you don't consider the di, so it would be methyl. So you can see here, even though it says dimethyl, which is before ethyl and isopropyl, if we were considering the di prefix, but for any prefix like di, tri, tetra, we don't consider it when alphabetizing. So we would consider the M in methyl when alphabetizing. So you can see here you have 4 hyphen ethyl to signify that ethyl is on carbon number 4, the isopropyl is on carbon number 5, and then there are dimethyl, so 2 methyl groups on and they're both on carbon 3. So you write 3, 3 to show that there's 2 methyl groups on carbon number 3. So that's just like a general example on how to find the complete name of this compound. Any questions before I move on to a problem? You can either put in the chat or just unmute. And Chris is also helping out today in the chat if you want to post any questions. Okay. And no one has any questions, I'm going to give you guys this problem. So what is the IUPAC name for the following structure? So for the structure on the right, what would its name be? I'll give everyone a few minutes for this. Let me just start the poll. Okay, all the answers are anonymous, so take your best guess if you're really not sure, or hit, I have no idea. All right, I'll give everyone a few minutes for All right, I'll give everyone about 15 more seconds if you want to get your final answer in. All right, I'm gonna stop the poll now. Okay, so everyone click choice A, and yeah, that's the correct answer. So in this one, the longest chain is pretty obvious. It's this one in the middle. So it has 7 carbons, so it'd be heptane. And with the 2 methyl groups coming off of it, you have to signify that you have to show that there's 2 methyl groups, so you have to put the dimethyl. And then when numbering the carbons, you want to start numbering from the right side. So this rightmost carbon would be carbon 1, and then the methyl group would be on carbon 2, and then the other one would be carbon 5. So you show that there's a carbon on carbon 2, there's a methyl group on carbon 2 and then carbon 5, and that's because it would assign lower numbers to those 2 methyl groups instead of numbering from the left side, which would give it 3. So 2 and 5 is lower than 3 and 6 if you start numbering from the left side. Any questions on this problem? Okay, all right, let me move on. So next I'm going to talk about isomers. So isomers, these are molecules that have the same molecular structure, but then they look differently based on their connectivity or how they are in their rotations. So the first isomer I'm going to go over is structural isomers. So these are the least similar of all isomers. They only share the same molecular formula and weight. So they have the same chemical composition. So they have all the same chemical makeup, but then they have different chemical properties and also physical properties. So when writing them, their formula, they'll look the same, they'll have the same molecular weight, but when drawing them out or writing their IUPAC name, they'll have major differences. So as you can see on this right side, these 3 molecules, they all have the same chemical formula and molecular weight because they're made up of the same elements and the same amount of each element. But because of their connectivity, they all look pretty different, and that leads to them having different chemical properties as well. So these are structural isomers. They're the least similar of all isomers. Next, I'm going to go into stereoisomers. So these are more similar than the structural isomers. They do have the same chemical formula, but they also have the same atomic connectivity. So these will have the same bonds, but they just differ in how the atoms connected to each other are arranged in space. So when I go over their connectivities, usually they draw the molecules using wedge or dashed lines or solid lines. So within a solid line, we assume that it's like flat against the page, but for wedge lines, we usually assume they're coming out of the page, and dashed lines that they're going into the page. So stereoisomers, these include all the isomers that are not structural isomers. So stereoisomers, they include conformational isomers and configurational isomers. So these isomers, they're still different, but they're more similar than the structural isomers that just share the same chemical formula and molecular weight. These have the same connectivity. They just differ in how they're connected the same, but it just differs in how the bonds look when they're connected. So the first stereoisomer is conformational isomers, sometimes also known as conformers. So these are the most similar of all isomers. They're basically the same molecule, but they're at different points in their natural rotation around a single bond. So single bonds, they're unlike double or triple bonds that they can move about. They're not as rigid as single and double bonds, so the molecules can rotate while connected to each other in single bonds. So like I said before, they vary in the degrees of rotation around a single bond, and this creates different levels of strain. For conformational isomers, they usually use what is known as a Newman projection. So that is the two molecules on top. So the ones with the circle and the lines, those are known as Newman projections, and they're usually used for conformational isomers. This is because this allows the molecule to be visualized along a line extending through the carbon-carbon bond axis. So the circle represents the bond between the two carbons, and then where the three lines meet up, that's the carbon. So on you can see there's where the three lines meet up, that's on a carbon, and then on the other side of this circle, you can assume it's the other carbon that's attached to the carbon that you can see here. So the Newman projection, it looks directly across the bond from carbon to carbon. And this is done to show how the three substituents connected to the carbon-carbon bond, how they stack up to each other and how they look as the bond rotates. So on the top left molecule, you can see that the carbon-carbon bond, the substituents are on top of each other. So this creates more strain on the bond than if it was at the rotation on the right side, where all the substituents, they're separated from each other equally. This would be more favorable because the substituents aren't directly on top of each other, creating strain on the single bond. And then on the bottom, it's a more detailed representation of how the bond looks between the two carbons. So instead of looking directly across the bond, this gives like a bird's eye view of the bond between the two carbons. So these are conformational isomers. So the left and the right, they're both the same molecule, but they just differ in how the bond rotates. So at which point of the bond rotation these two molecules are in. So that's conformational isomers. They have different conformations that they can be in. So the first is a staggered conformation. So this is when the substituents aren't directly on top of each other. They're separated from each other equidistant. So like I said, there's no overlap of the atoms along the line of sight in a Newman projection. They're each substituent is in between the two substituents on the other side of the bond. The first type of staggered is anti-staggered. So this is when the two largest substituents are anti-periplanar. So this is when they're on the same plane, but on opposite sides. So as you can see on the bottom, the two big methyl groups are on the same plane, since they're both a solid line, but they're anti because they're directly across from each other. They're on opposite sides. This is pretty favorable because they're not in each other's space. There's not a lot of strain on the single bond. They're given as much space as possible because the hydrogen bonds are a lot smaller than the methyl groups. So because the two methyl groups are directly across from each other on opposite sides, this is pretty favorable. There's not a lot of strain on it. Gauche is the next conformation. It's also staggered, but it's not as energetically favorable as anti, because there's only a 60-degree difference between the two largest groups. So I can see on the top, this gauche formation, the carbon groups are still not on top of each other, but they are pretty close to each other. They have a 60-degree difference between them instead of the 180-degree difference between the methyl groups and the anti-conformation. So those are the two different staggered conformations. When the substituents are on top of each other in the Newman projection, this is called the Eclipse Confirmation. So for just Eclipse Confirmation, this is when the two methyl groups, or the two largest substituents, they're 120 degrees apart, but they still overlap. So there's an overlap of the hydrogens on the adjacent carbons. So as you can see on the bottom figure, the substituents are on top of each other, but the methyl groups are still 120 degrees away from each other. This is more favorable than what is called totally eclipsed. So this is when the methyl groups are directly on top of each other. There's 0-degree separation between them. And this has the highest energy state because of the strain caused by the two methyl groups being right on top of each other, but it's energetically unfavorable because of how much strain there is on the molecule. It's not favorable because of that. So when the two methyl groups are on the same plane on top of each other, this is what is known as syn-periplanar instead of anti-periplanar. So they're on the same plane on the same side, and this causes the total eclipse conformation. So for these conformational isomers, they can interchange between each other because of the small amount of energy needed to rotate a single bond. So just a small amount of energy is needed to convert from the staggered and the eclipse conformations. So a molecule can interchange between them. And this is why they're pretty similar, because they're the same molecule, but just because of the bond rotation causes these conformational isomers. Any questions before I go on to chirality? You can put it in the chat or just unmute. Do we say less steric hindrance? Yeah, you could say that. Steric hindrance is more about bonding, but it's more, yeah. So steric hindrance is more about like anything for like bonding purposes or like ring purposes, but you could say that about the methyl groups on top of each other. It's just it creates more strain on the molecule. Do you need to know when the gauge formation is more stable than the anti formation? So for anti and gauge, so for, yeah, there would be a few exceptions depending on what the group is, what the groups are attached to the carbons, but usually anti is more stable just because the two highest functional groups are on the opposite sides of each other. Okay. Oh, sorry. So next thing I'm gonna go over is chirality. This is needed before going into the other staggered isomers known as configurational isomers. So for chirality, a molecule can be considered chiral if the mirror image can't be superimposed on the original molecule. So this means the molecule lacks a internal plane of symmetry. So if you cut a molecule in half and it's symmetrical, then it would be considered chiral. And this is important because this determines what kind of how many different kinds of configured isomers a molecule can have. And if a molecule is chiral, it can interact with and polarize light. So we can say for a molecule that's chiral, it can have optical activity. And a molecule is considered achiral if it can be superimposed on the mirror image. So if a molecule only has 3 different substituents on a carbon, then the carbon is considered not a stereogenic center. So a stereogenic center, otherwise known as a chiral center, this is a carbon that has 4 different substituents attached to it. It is asymmetrical and the core of the optical activity. So because of this chiral center, it can give a molecule optical activity and polarize light. And this is, like I said before, it's only considered a chiral center if it lacks a plane of symmetry. So if you see the figure on the right, the ones with a chiral center, they have 4 different substituents bonded to it. So for this left chiral center, you can see that it has 3 different chains attached to it. And then you can assume there's a 4th bond to a hydrogen. So all those 4 substituents, they're all different. Same thing for the chiral center in the middle. It's bonded to 2 carbon chains, a hydrogen, and then this chlorine molecule. So since these are all 4 different substituents, it can be considered a chiral center. But then this arrow on the right, it's pointing to a carbon that's not a chiral center because it's bonded to 3 carbon chains, but 2 of them are methyl groups, which are the same group, and then a hydrogen group. So it would only have 3 different substituents, which wouldn't make it a chiral center because it needs 4 different groups. So any molecule with at least 1 chiral center can be considered chiral if it also doesn't have a plane of symmetry. So to figure out the absolute configuration of a chiral center, you have to assign a priority to the 4 substituents. So those are the 4 different groups attached to the chiral center, and you have to do this for all the chiral stereogenic centers. So when considering priority, you assign the atom connected to the carbon with the highest atomic number with the highest priority. So usually the bigger molecules attached directly to the chiral center will be given higher priority. So you assign it the highest priority. So usually I signify that as 1. So I would give 1 to the atom with the highest atomic number. But if they're, let's say, both attached to carbon, if there's 2 groups with carbons directly attached to the chiral center, then you can determine the priority by the other molecules attached to it. So look at the next molecule. If they're both attached directly to a carbon from the chiral center, then look at the other carbon, the other group attached to a carbon. So if one carbon has another carbon attached to it, while the other one has a nitrogen attached to it, then the one with the higher atomic number attached directly to that carbon has the higher priority. So when they have the same priority, then you move the same atomic number, then priority is determined by the rest of the atoms attached directly to that substituent. And for double bonds, you have to count them as 2 individual bonds, and then triple bonds, you have to count them as 3 individual bonds. So if it's a carbon is double bonded to another carbon, then you have to count that as 2 single bonds to a carbon. And for triple bonds, same thing. If a carbon is triple bonded to another carbon, then you have to count that as 3 single bonds to a carbon when counting priority. And likewise, if it's still a tie, to determine the priority, you have to keep working outwards from the stereo center. So consider the other molecules attached to that carbon. So usually what I do is I have the lowest priority group in the back while the other 3 substituents radiate out of the page. So I would give the 3 higher priority substituents either a solid line, or you can use a wedge line to signify that they're not pointing towards the back, pointing either along the page or out of the page. And then the lowest priority functional group, you can have that as a dashed line to show that it's pointing into the page because it has the lowest priority. Usually it's like a hydrogen group. Those usually have the lowest priority. So it's usually a hydrogen group sticking into the page. And then, so to show the absolute configuration of the chiral center, you draw a circle connecting the substituents from highest priority to the next priority group. So you would go from 1 to 2 to 3, and then the 4th priority group, which is the lowest one, would be the ones sticking into the page, so you don't count that when drawing the circle. And this is to determine if it's an R or S configuration for that chiral center. So for S, it's an S configuration if the circle that you draw is a counterclockwise circle, and then an R configuration if it's a clockwise circle. So in this diagram below, you can see that the highest priority group is on the bottom left side. The second highest is pointing up, and then the third highest is pointing to the right. So when you draw a circle, you connect 1 to 2 to 3, and that shows a clockwise circle. So that would be R configuration. And then for S configuration, it would be opposite. So starting from 1, if you draw a circle from 1 to 2 to 3, this one on the right, you can see the circle goes counterclockwise. So that's an S configuration. So usually I remember this by how I write an R and S. So when you begin writing an R, when you begin writing like that half circle in the R, you go clockwise. So this is how I think of it. So when you draw an R, you go like this, right? So you're going clockwise when drawing an R. And then for S, when you start to write an S, you go counterclockwise. So when you have to determine if it's R or S, when you have the functional groups, try to remember how you write an R or an S and which direction that goes. And that will help you determine if it's R or S, depending on if the circle is clockwise or counterclockwise. So for S, the circle has to be counterclockwise, and then for R, it has to be clockwise. So after you determine the priority of the functional groups, have the lowest one sticking into the back. So don't consider that when drawing a circle. And then when you draw the circle from highest to second highest to third highest, if it's a clockwise circle, it's an R configuration. And then if it's a counterclockwise circle, it's a clockwise counterclockwise circle, it's a S formation. Let me get rid of this. Okay. Oh, sorry. So for this question, which of the following is a chiral molecule? I'll give everyone a few minutes for this. Let me just start the poll. Okay, I'll give everyone a few minutes for this. Take your best guess if you don't know. Oh, sorry, yeah, so this bottom left choice is choice B. All right, I'll give everyone a few more seconds, 15 more seconds on this question. Okay, I'm gonna stop the poll now. And it looks like we have some mixed answers. So the correct answer is is choice B. So for choice A, you can see that there are 3 stereogenic centers. So the 3 carbons attached to the methyl groups, they're all possible stereogenic centers, but if you remember, I said a chiral molecule can't have the plane of symmetry. So if you take this molecule, and cut it down the middle like this, sorry, that was bad. Yeah, if you cut it down like this, down these 2 carbons, it's a symmetrical molecule. So that would not be chiral because it has that internal plane of symmetry. Likewise, for choice C, if you cut it down these 2 carbons, you will have a symmetrical molecule. This H, they put it on the side, but you can think of it, the H as here. So when you cut it down the middle, it would also, both sides of this plane would be symmetrical. So a chiral molecule can have stereogenic centers and not be chiral if there's an internal plane of symmetry. And then for choice D, you can cut it down in this plane right here. So, and then it would be symmetrical on both sides. So if this molecule, you can draw a line and both sides of it are symmetrical, then it's not considered a chiral molecule, even if it has chiral centers. So these carbons right here, they're chiral centers, but this molecule as a whole is not a chiral molecule because of these internal planes of symmetry. But you see this one, it has these 2 chiral centers, and there's no way to draw a line through this molecule that would make it be symmetrical on both sides. So it doesn't matter if you draw it like this, both sides aren't equal. If you draw it like this, both sides aren't equal. There's no way to draw a line through this molecule that would make it symmetrical on both sides. While these choice C and choice D, you can draw a line down these 2 and they would be symmetrical. Choice A, you can draw a line down this way and they would be symmetrical too. So it's not these. While choice B, if you draw a line down the middle, there's no way to make it symmetrical. Does everyone understand? Yeah, so Opal, yeah, I don't know if you saw, I drew so wherever the chiral centers are is where they have a carbon with 4 different substituents. So it would be those attached to the groups coming off of the ring in this problem. And double bonds are achiral because they are only bonded to 3 different things. Because of the double bond, they have 1 less bond than a sp4 hybridized carbon. So these, let me try. So these carbons right here, they would not be considered stereogenic centers because they're only attached to 3 things instead of 4 because of this double bond right here. But these 2 are stereogenic centers because of the 4 different things that are attached to it. It has the ring that it's attached to, and then this methyl group, and then also a hydrogen atom that is usually not drawn in these drawings. Same thing for the other stereogenic center. And then because there's also no internal plane of symmetry, this molecule is considered chiral. Does that make sense to everyone? Anyone still having difficulty with this?
David, could you go over D?
Sorry, Opal, you said
Yeah.
D or you said
D, dog.
Okay. Yeah, sorry, Opal, you're still echoing a little bit, but yeah, I can go over D. So D, these two carbons right here, they would be the stereogenic centers because it's attached to this. It's attached to this group, and then the ring also, and then also a hydrogen atom that is not drawn. So both of these groups, both of these carbons, are attached to this alcohol group, and then the ring, which gives it two other carbon bonds, and also a hydrogen group. So because they're both attached to four different things, they're considered stereogenic centers. But this molecule is not chiral because if you cut this molecule down this line, this plane, you cut it down using this plane, both sides of this molecule are symmetrical if you cut it down this plane. Let me try to redraw it so it looks a little better. So if you cut it down this line, both sides of this molecule are symmetrical. So it has this internal plane of symmetry. It just looks a little bit weird because the alcohol groups they're not like drawn perfectly symmetrical, but they if you look at it without like looking at how the alcohol group is drawn, you can see that they're both attached to the same alcohol group and they're both wedged. So they have the same configuration. If you cut it down this line, it has this internal plane of symmetry. So molecules with an internal plane of symmetry, even if they have stereogenic centers, is considered achiral, if that makes sense. Okay. Anyone else have any questions? Okay. All right. So I'll move on to the next topic. Let me just erase this. Okay. So next thing I'm going to go over is configurational isomers. So this is also a type of stereoisomer. So this is when two different molecules can only be changed from one form to another by breaking and reforming covalent bonds. So this is what I was talking about when we needed to know like R and S and also the wedge, dashed, and solid lines. So there are two different types of configurational isomers, enantiomers and diastereomers. So when looking at configurational isomers, you have to note that wedge lines are the ones that point out of the page. So if you're looking at a solid plane, it's the one pointing out. Dash lines are the ones that point into the page, into the plane. And then solid lines are the ones that are parallel against the plane. So the solid lines would be parallel against your screen right now. So the first type of configurational isomer are enantiomers. So these are non-superimposable mirror images. So a classic example is your hand. So your hands, they look the same, they look identical, but if you flip it over, you can't put your hand on top of your other hand to make it symmetrical. So even though your hands, they look alike, you can, if you flip over, mirror image, if you take your hand and you flip it over, you can't superimpose it on your other hand, even though they look identical. So usually when you hear non-superimposable mirror images, you think of it in enantiomers. So these molecules, they have the same connectivity of their atoms, but they have opposite configurations at every chiral center. So meaning if an enantiomer has all R configurations, if an enantiomer has all R configurations, the other one will have all S configurations. So it'll have all the opposite configurations. So like I said, they since they're all connected the same, but they just have opposite configuration at the chiral centers, they'll have the same chemical and physical property, but not the same optical activity or reactions in chiral environments. So that means because they have opposite configurations at the chiral centers, they'll have opposite optical activity. So the R and the S configurations at each chiral center will determine the properties of the enantiomer in chiral environment and when trying to polarize polarized light. So you can consider a molecule optically active if it has the ability to rotate a plane polarized light. So when considering a molecule's optical activity, you have to consider their R and S configurations at the stereogenic centers. So if a molecule has R activity, it'll rotate plane polarized light a certain degree of rotation, and then the enantiomer, since it'll have the opposite configuration, so instead of R, it'll have S, or instead of S, it'll have R. It'll rotate it the same amount, but in the opposite direction. Going further into optical activity, you can consider a molecule dextrorotatory, or D, if it rotates a plane polarized light to the right or clockwise. And it can be an enantiomer can be considered level rotatory, or L, if it rotates light to the left or counterclockwise. So remember, clockwise as plus. I usually try to remember it as like positive, like that's how a clock normally goes, and then counterclockwise or negative, which I think of it as the opposite direction a clock goes. So the direction of rotation can't be determined just by looking at the structure of these molecules and compounds. It must be determined experimentally. So the MCAT, they can't have you determine which direction it rotates. Usually they'll tell you in the passage. So at the bottom, I just included a figure that goes more into detail about optical activity. So normally there's a light source, and then if you have a molecule in front of the light source, it will rotate a light a certain amount. So any molecules with a chiral center, there will be optically with a chiral center and chiral, it will rotate the light a certain amount based on the structure of the molecule and the R and S configurations of that molecule. So for enantiomers, one enantiomer will rotate light a certain amount, and then its enantiomer that's opposite, that has the opposite configuration, it'll rotate the same degree, but in the opposite direction. So just remember that enantiomers, they have the same connectivity, but just opposite configurations at every chiral center, and that causes them to rotate light the same degree, but in opposite directions. So that's enantiomers. And then there's also a specific type of enantiomer known as a racemic mixture. So this is when you have equal concentrations of the positive and the negative enantiomers. And like I said before, they rotate the same amount of degree, they have the same degree of rotation, but because they have opposite R and S configurations at every chiral center, they rotate in opposite directions. And because of that, a racemic mixture is when you have 50% of each enantiomer. So 50% of one enantiomer, and then the other 50% is the opposite enantiomer with the opposite R and S configuration. When that happens, the rotations in plane polarized light cancel each other out. So there's actually no optical activity observed. So it won't won't rotate plane polarized light. So even though them separately, each of these two molecules separately would rotate plane polarized light, but because it's a racemic mixture, there's 50-50 of both molecules, they cancel each other out. So one will rotate, let's say, like 50 degrees in one direction clockwise, the other will rotate 50 degrees in the opposite direction counterclockwise, and because of that, they cancel each other out, and you actually get no optical activity. It won't rotate plane polarized light. But this is only when you have 50-50 of each molecule, and this is known as a racemic mixture of enantiomers. And then the next type of configurational isomers is known as diastereomers. So these are also non-superimposable mirror images of each other, but when enantiomers, they are opposite configurations at each stereogenic center or chiral center. Diastereomers only differ at some but not all the centers. So a diastereomer will have 2 or more stereogenic centers, but they will differ at some but not all the centers. This allows there to be 2 to the n power possible types of diastereomers for a molecule when there is n chiral centers. So if there's 2 chiral centers, it would be 2 to the 2, which is 4. There would be 4 possible stereoisomers. And because diastereomers, they differ at some but not all the centers, each different diastereomer can have different chemical properties and different arrangements in space. So while enantiomers, they differ at all the chiral centers, diastereomers, they differ at not all but some of them. So as you can see here on the bottom, on the left side, there's 2 chiral centers. One's an S configuration, one's an R configuration. On the right side is its diastereomer because it differs at the bottom chiral center. So the R becomes an S, but the top chiral center is still an S. So they differ at one, but not both of the chiral centers. So if they were to both differ, so on the left side is S and R, if the right side were to become R and S, so the top one is R and the bottom one is S, they would be enantiomers because they differ at all the chiral centers. So that's diastereomers. There is another subtype of diastereomer called geometric isomers or cis and trans isomers. So this is when a diastereomer has substituents that differ in position around an immovable bond, so a double bond or a ring. So like I said, a single bond, it can rotate, it can move. A double bond and a ring, they're pretty, the bonds are immovable, so they wouldn't be able to rotate. So these substituents, when bonded, they stay on the same side of the bond, they won't rotate. So we think of it as like an immovable bond between the 2 carbons with a double bond, so that bond can't move. So when the substituents are on the same side of an immovable bond, then we think of it as cis, as in like same. And then if the substituents are on opposite sides of the double bond, we think of it as trans. So when you think of a double bond, you think of this as an immovable bond. So this line across is the line that differentiates if it's a cis or a trans isomer. So since these 2 methyl groups, they're on the same side, then this would be a cis isomer. So it would be known as cis 2 butene. But then if you draw this line on the right side, the methyl groups, they're on different sides of this double bond. So this would be known as trans 2 butene. So these two, they're the same molecule, they have the same connectivity, but they just differ on which side the substituents are on the carbons involved in the double bond. So this is a subtype of a diastereomer, otherwise known as a geometric isomer or cis-trans isomer. All right, moving on. And when, so cis and trans are usually used for monosubstitute double bonds, but when there are multiple substituents attached to the carbons involved in the double bond, then we usually use E or Z. So E is if the two groups of higher priority are on opposite sides of the double bond. So E would be related to trans, since the groups are on opposite sides of the double bond. And I like to think of E as being on opposite sides of the bond, because E sounds like I think of E as like opposite, which just sounds like opposite. And then Z is analogous to cis. If the two groups of higher priority are on the same side of the double bond, then you identify that as Z, Z as in same, which sounds like same. That's how I usually remember it. It's kind of dumb, but it helps me remember it. So I think of E as opposite and then Z as same. So this is for when there are more than one substituent attached to each double bond, each carbon in the double bond. So you'll see E and Z, and then cis and trans being used also. And then finally, there's a special group called meso compounds, and this is what we went over. So this is molecules that have chiral centers, but they have that internal plane of symmetry. So even though they have chiral centers that have 4 different substituents attached to it, because of this internal plane of symmetry, there is no optical activity, and it won't rotate plane polarized light. So the plane of symmetry can be through a chiral center or between a chiral center. So you can cut it through a bond between two molecules, or you can cut it directly down the middle of the atom. So this is the equivalent of racemic mixtures, because there is no optical activity or rotate plane polarized light like racemic mixtures. So they're both optically inactive and won't rotate plane polarized light. Any questions on this before I give you guys a problem? Okay. Yeah, so diastereomers can have different chemical and physical properties, while enantiomers will have similar properties. If anyone has any questions, you can put in the chat or just unmute. All right, if not, I'll give everyone this question. Take a few minutes. Let's start the poll. All right, take a few minutes. Sorry, the image is a little bit blurry. All right, I'll give everyone a few more seconds before I close the poll. Okay, I'm gonna close the poll now. And pretty spread out, but most people got it. Answer choice is B. Yeah, so as you can see, these carbons in the circle, these are the stereogenic centers. They have the 4 different substituents bonded to the carbon. And if you remember, I said for stereoisomers, to find out the possible stereoisomers, you use the formula 2 to the n. So n is the number of chiral centers, and since this molecule has 2 chiral centers, it would be 2 to the n, so it'd be 4. So there would be 4 different stereoisomers. So this is because the 4 different stereoisomers they can be both RR configuration or SS configuration or RS configuration and then SR configuration. So those are the 4 different stereoisomers for this compound. Any questions about this problem? Okay. All right, if no one has any questions, here's another problem. Give everyone a few minutes for this too. Just restart the poll. All right, take a minute or two to look at this question. All right, I'll give everyone a few more seconds on this. Okay. All right, I'm gonna end the poll now. And most people click choice B, and yeah, that's the correct answer. So meso compounds, they have chiral centers or carbons that are chiral, but the whole molecule as a whole is considered achiral because it does have that internal plane of symmetry, which would make it achiral as a whole. Anyone have any confusion on this question? Yeah, so if no one has any questions, is the end of the lecture. Anything in this lecture as a whole that you're confused about or have any questions on? Thank you everyone for attending. Thank you, Chris, for helping out, and everyone in the chat. Yeah, and then tomorrow, if you want to tune in for Friday's lecture, I'm going to stop the screen share now and pause the recording.